me send a message. Maybe this person tells me there, do we know you? Because what I used to do was to keep everyone in waiting room so I could manually enter everyone. Today I haven't done that. I think fairly high. Cool. I'm gonna make it now, put participants in waiting room on entry so that this person does not come back in. Okay, great. Cool. Any questions about last class? So we are going to have 2 more classes today and the one on Thursday. And that's it, then you're done. So let's share my screen. And we have a few presentations left. I know Becca is left. Thomas is left, I think. So we will finish those in a while. Okay, so I want to start again by talking a bit about susceptibility and long-range correlations. So the key formula that we derive, and also talk a bit about what happens below critical temperature and happens close to critical temperature, because those things are subtle and quite important. So last time the key formula that we derived was chi, which is defined to be 1 over n. How does the average magnetization change with respect to temperature multiplied by applied field at constant beta? So beta you could pull out, nothing really matters there. And that itself is the same as looking at the fluctuations from the average magnetization. So this formula is quite important, and that's the definition. This on the first is the definition of susceptibility, and this over here is something you showed in homework 5, which is very much like heat capacity we did for canonical ensemble. So then, I'm recording again. So then what we showed was that chi is equal to mu square summation j is equal to 1 to n C1j. This was super important. And C1j here, or Cij in general, is defined as the correlation between 2 spins, average value of SISJ minus average SI minus average SJ. So this showed us that long range correlations are the same as, I would write correlated with susceptibility, but that would be a strange sentence, are equivalent to diverging susceptibility. Because when chi diverges, or when in thermodynamic limit, when n tends to infinity, and if C1j is non-zero, which means that spins on an average are correlated with each other, and then as you take the n tends to infinity limit, the right-hand side in equation 1 will diverge, which means the susceptibility in the left-hand side will also diverge. So then we try to understand this, what does this divergence of susceptibility? But another way of looking at it is the presence of long-range correlations. That will be a bit more intuitive if you think of it that way. What does it mean for the system to have long-range correlations below critical temperature, well below critical temperature, and very close to critical temperature? What does it really mean? So, and there we showed that T less than Tc, what really happens is the average magnetization versus H plot looks something like this. So right at H is equal to 0, you have a divergence. So if you think of this divergence, this equation here diverges. It blows up. So you have a slope that increases very fast from negative to positive magnetization. And this you know is true because when you apply a very strong magnetic field, you will get everything stuck in one sign. at very close to TC, the things become a bit different. There, the main physics that happens is that when you think about this potential of mean force of magnetization versus magnetization, it is this barrier that starts to go down as temperature increases. No barrier at T is equal to Tc. So essentially the system can reversibly move between positive magnetization and negative magnetization without any barrier. It has no problem in moving back and forth. So in this one, the idea was that any H more than 0 will quench the system into a magnetized state where everything is pointing up or everything is pointing down. So I want you to go and look at Formula 2. And this is something I thought I would go over again because it's a bit counterintuitive at first chance. If you think that every spin is pointing up, what should be the value of Cij if we know for a fact that every spin is pointing up? What do you think? Anyone? Luke, what do you think? If every are guaranteed to be 1.
I'm not quite there yet, I think.
Okay, anyone wants to help me? If every Si and Fj are guaranteed to be 1 or positive, let's say 1, what is the value of Cij?
It would just be 0.
It will be 0. There is no correlation, right? So it's kind of funky that you think that every spin is pointing in the same direction upwards. So the correlation should be very high, but not really. Cij is 0, right? So this is kind of counterintuitive. You have to think about it. So you don't really have correlations here. Nothing's happening. You are quenched. Correlation means that if I change one thing over here, other things will respond way out there. But there is no response here. Everything is forced to be 1, period. Nothing is going to happen. It is only in this regime, very close to 0 magnetic field, and my screen froze. That's annoying. So it is only in this regime where you can have long-range correlations. Here, on the other hand, it's funky. For any magnetic field you can continue to have for any value of H, things can be correlated with each other. And this is where the system starts to look like a fractal. Things will be correlated at all length scales. So close to T, and if you go up a critical temperature, then it's another story. Then we are not going in that regime. We are talking about things below critical temperature, but slightly below. We have correlations at all length scales. And a fractal is ridiculously hard to draw, but I'm sure you have all seen fractals at some point. At all length scales. Fractal systems also tend to be chaotic. You change one thing and everything falls off in bizarre ways. So that's the key difference that you need to understand. So the point I'm trying to drive home here is just because everything is pointing up, that does not mean the system has long-range correlations. That just means that Cij is 0, nothing's going on. It's only in this regime that you have a change in the average magnetization from negative to positive, and that's why the susceptibility diverges. And it is only here that you can have long-range correlations. Here, on the other hand, long-range correlations will exist for any magnetic field, and you can keep applying more and more magnetic field. It will not get rid of the long-range correlations. And that is what Chandler says in that figure. So you should go back and read that figure and the accompanying text again. He says that below critical temperature, even if you have long-range correlation, as soon as you turn off gravity or any external magnetic field, it's gone. Close to critical temperature, it will keep existing in all sorts of funky ways. And that is kind of the theme of one of those papers that I put it as in the set B regarding comparisons with stock market. That's the kind of argument he's trying to give there. If you're very close to critical temperature, You can think of the Federal Reserve Bank as an external magnetic field. You know, that's what's happening right now. You're putting in ridiculous amounts of money, right? Sometimes I think, what does it mean to put $1 trillion? Where is all this money? We're creating debt in the future. You put all this money, but is it really going to get rid of these long-range correlations? Is it going to reduce the system from its chaotic behavior? If you're not at the critical point, it will. But if you're at the critical point, it won't work. So that guy who wrote that paper is actually a hedge fund manager who thinks about things like this. So I thought that was interesting. You don't have to read that paper, but these critical point type funky behaviors, you don't have to go to stock market to find them. They show up in all sorts of aspects in nature. Now this, oh, my screen froze again. That's not right. So stop share. Sorry about that. So this notion that correlations exist at all length scales is the, oh, so Tyler sent me a message. It was Tyler who I kicked out. Well, he didn't respond, so just give me a moment. Well, you can't blame me, Tyler. Sorry, I have removed the waiting room. Sorry about that, I have removed waiting room. So in general, it's a good idea to keep your real name in Zoom for a variety of things, as you can see from this experience. Okay, sorry about that. Okay. So we know it wasn't a bot, so that's good. So close to critical temperature, we have correlations at all length scales. And so in a sense, we have a self-similarity. So if you think of an Ising model with plus spins, down spins, plus spin, down spins, and things like this, what this is really telling you is you could look at one spin at a time, or you could look at a block of 4 spins at a time, or you could look at a block of 9 spins at a time. Not much is going to change because the system is long range correlated. It will act in the same way. So that's the nature of a fractal, right? You have, I mean, I'm really not going to try to draw a fractal, but that's what happens in a fractal. You can keep zooming in. The landscape does not change. I mean, the best example is the beach along an ocean. You can look at it from an airplane. You can go down there and look at it. It's kind of the same jagged thing that goes on and on. Of course, we'll go to the atomic level and then everything becomes ordered. But across lots and lots of orders of magnitude, it is the same. So this thing led to the basic ideas behind the thing we are going to study now, which is called renormalization group theory. So renormalization group theory actually does involve groups from abstract algebra. We are not going to go into that. We are going to just look at it from a very one lecture perspective and try to get a flavor for what's going on. It was actually proposed in quantum field theory very early on, like 60s or even 50s, but it became really popularized by Ken Wilson, who got a Nobel Prize in 1971 for renormalization group theory. He did his PhD with someone whose name you might have heard. I don't know. I think this is the correct spelling. Does anyone know this name and why he's famous? Murray Gell-Mann? You know what he invented or discovered? Someone should know. Where is Ben? Is Ben sleeping still?
Like, what are you talking about? The eightfold way thing?
Eightfold way sounds like the Buddhist philosophy. Even something fundamental, quark.
Yeah.
You're right.
Yeah, the quarks.
He predicted the quark theoretically well before it was invented. He just predicted that it would exist. So Ken Wilson worked with him, and then he was an undergrad at Caltech, and then he went to Cornell and worked on the renormalization group theory, which led to Nobel Prize. I don't know if he got the Nobel Prize in 1917, but even before Ken Wilson, the idea for renormalization group theory had existed, and two people had worked on it. One was Leo Cardanoff at Cornell. He recently passed away. You can watch his videos on YouTube. He used to bike to Cornell every day, even in age 80s, and work until his last days, I think. And the second person who really worked on this is someone very close to us, whose name is Michael Fisher, who was someone who would teach 687 until a few years ago. And Michael Fisher and Leo Cardanoff did not win the Nobel Prize for this, but they did win the Wolf Prize, which is very prestigious, in 1980 for the same thing. And what Ken Wilson did was to put their idea in a framework which is actually used. Now, Michael Fisher has a reviews of modern physics article on this, talking about, I will send you some articles on renormalization group theory so you can read on it. And Kardanoff has an American Journal of Physics article, and that's what we are going to follow today closely. So the idea in renormalization group theory is quite simple and quite beautiful. It says that if things are going to look similar, even if you keep changing the length scale, why look at the smallest length scale? Why not start kind of zooming out, right? So the term that is used for renormalization group theory is a verb I like a lot. It's called decimation. So you start decimating degrees of freedom. You say, well, instead of looking at this red one at a time, I'm going to look at this black one at a time, all four of them together. I will look at their average properties. And then why stop there? Why not just look at all 9 of them together at the same time and things like that? And we will formalize all of this. And I'm going to call it as RG theory. That's quite common. So what RG theory does is to decimate or remove certain degrees of freedom. There is an obvious advantage of doing this. Your number of degrees of freedom goes down, right? You were dealing with a system with n degrees of freedom. Now you will be dealing with a system with half the number of degrees of freedom. So your calculation should be simpler. But there is a catch. Once you reduce the degrees of freedom, this spin was talking to this other spin through a simple energy function, right? SI dot Fj multiplied by J. What is the guarantee that this block of spin is going to talk to this other block of spin through the same energy function? It's going to be more complicated. For example, and you can see how this is, and just to give you a sense, like, let's say we are all spins. I am a spin, Luke is a spin, Ben is a spin, Thomas is a spin, and we talk to each other, but we have a lot of us on the planet. A billion people is hard to deal with. So decimation sounds bad in terms of human, but we average out. We look at Ben and me and Thomas and Luke together, interacting with Pawan and Jess and Emily together. The way in which groups of humans talk to each other is not going to be the same the way in which humans talk to each other. This is something we know from personal experience, right? The interactions change completely. What renormalization group theory does is to try to keep interactions same or similar. And that's the hard bit, how to do that. So how to produce such a decimation that the energy functional does not really change. So that's what we are going to do now. And before we do that, I want to show you some of the things it can predict. So when you have these phase transitions, a lot of funky things happen close to critical temperature. For example, the heat capacity of the material, which we have studied heat capacity in great detail in the first part of this class, where we remember all those beautiful plots that you made, Einstein and Debye and everything. But close to phase transition, things can be funky. The heat capacity can diverge. And the other side of the critical temperature, it might look like this, that you can have all sorts of bizarre behavior. And these curves which describe the divergence of the heat capacity are quite universal. These curves are typically described by what is called power law. So as you advance in your scientific careers or even social careers, these are terms that you will see often used in conjunction with each other. They show up at the same time. Power law, chaos, fractals, self-similar. Mostly these four terms tend to apply to systems with the same physics. And that physics typically ends up being that you are close to the critical temperature. Did I include Bialec's paper in the exam? Let's see. Oh, I should add that paper. That's sorry, let me check. So final. Oh, I did not add that paper. Okay, I'm going to add one more paper in set B. I was a bit worried about it because it's a long paper. It's not really the same length as the papers in set B, but you can still browse through it. So this is a paper by a biophysicist at Princeton named Bill Bialek, where he says that perhaps all biological systems are very close to their critical temperature. So the title of this paper is Are Biological Systems Poised at Criticality? He makes this conjecture that maybe the reason why our bodies function the way they function is because in a certain strange way, we are close to critical temperature. I've added it to the folder. You can work on this paper also if you want. So renormalization group theory can give you this exponent very, very accurately. And that's quite powerful. It's hard to measure in actual experiments, but you can go and measure it. And this theory comes and tells you the value of this thing very accurately. So for example, this value for alpha in 3D Ising model is exactly or quite close to 0.125. And you can get it out of renormalization group theory. You can't do it exactly, remember, because Ising model in 3D, if you do it exactly, you will get a Nobel Prize, or I give you $10,000. If you do it exactly and still don't give a Nobel Prize. So let's see how it works in full mathematical detail. Poor Tyler, I don't think he was able to get in. Tyler, did you come back? Oh, that's sad. I guess he hates me now. That's sad. You can watch the lecture. So let's start. So in order to see renormalization group theory, we will start with 1D Ising model in absence of an external magnetic field. So at this point, you might go like, well, what are you trying to do here? In 1D Ising model, there is no phase transition. So what will we get in here? Well, I will show you the basic picture of how renormalization group works. I will show you how renormalization predicts that there won't be a phase transition. Because if you might recall, mean field theory, in spite of its use and power and everything, gets it totally wrong in 1D. Mean field theory says there will be a phase transition. Renormalization group theory, on the other hand, shows you there is no phase transition. And the same ideas, then I will give you a flavor for how it works in 2D, and I will refer you to Kardanov's paper as a supplementary reading, not for exam, to see how it actually works. So if you recall our energy Hamiltonian in this energy function in the system, it is given by e to the power minus j si dot sj, right? And let's assume only nearest neighbor interaction. So this thing is minus j S1, S2 plus S2, S3 plus dot, dot, dot. And I'm leaving dot, dot, dot in the very beginning because I don't want to worry about what happens at the boundaries. Let's say it's periodic boundary condition. So we will define a constant called K, which is given by J divided by KBT. Now, so let's write down our partition function. So Q as a function of beta and N can also be expressed as Q as a function of K and N, right? I'm changing from beta to K. That's all I have done. So this is J beta, right? Or in other words, I'm saying beta is equal to J by K. So instead of thinking in terms of temperature, like in a canonical ensemble, I'm going to think in terms of K. So this thing will be given by summing over all microstates, e to the power minus energy divided by KT, right? E to the power minus energy divided by KT. That's our partition function, exponential. But energy divided by KT is now...
Your screen is frozen.
Huh?
think your screen.
No, it's not. It's okay.
Oh, okay. Yeah.
Yeah. So this is exp because I can see in my own screen. So this will be exp k of s1 s2 plus s2 s3 plus dot dot dot. Does everyone see that? I haven't done anything profound here. All I have done is to say minus e nu over kt is equal to minus beta over e nu, which I have replaced by this thing, right? Because e nu has a j, and j multiplied by beta can be replaced by k. So we just get a k. So this was page number 3. Now let's go to page number 4. So in other words, what we have is that our Q of Kn is given by summation over all spins. S1 is S1, S2, S3, all of them taking values from plus minus 1. exp of K dot 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 plus S1, S2 plus S2, S3 plus dot dot dot. So this is our partition function. So let's look at this. And it's a 1D system, so we can draw it. It's going to look something like spin number 1, spin number 2, spin number 3, spin number 4, spin number 5, spin number 6, dot, dot, dot. So what renovation group theory says is to remove the even ones, remove number 2, remove number 4, remove number 6. So remove, and remove sounds like, what do you mean remove? Do I just go and erase my S2 and S3? No, it's a well-defined mathematical operation. Remove, or in terms of probability theory, we are going to marginalize even ones. We are going to average over them. So what does that mean? Let's write it down. So the same Q of Kn summing over all S1, S2, S3 can be written as exp of K multiplied by S1 S2 plus S2 S3 multiplied by exp of K S3 S4 plus S4 S5. I have done nothing profound here, right? I have just rearranged things. You see, S1 S2 becomes S1 S2, S2 S3 becomes S2 S3. Every term is showing up exactly the same, and thankfully we have E here, so nothing is wrong. Now you might sit and wonder if Boltzmann's formula did not apply and if energies were not e to the power minus something, none of these beautiful theories we have would exist, right? So the exponential is critical for things like that. It's a wonderful function. But now let's see something here. The S2 shows up only in this one. S2 only here. S4 only here. And this spins goes over all of them, all spins. This summation goes over all spins in values plus 1 and minus 1. So now let's go and actually sum over S2, values plus and minus 1. And then let's sum over S4, values plus and minus 1. And let's leave the S1, S3 as it is. So we are now going to write the summation as S1, S3, S5, S7, and actually perform the summation for S2. So how will that look like? That will now look like K multiplied by, when S2 is plus 1, it will be S1 plus S3. I should be careful with my brackets. Yeah. Plus exp K multiplied by S1 plus S3, but now S2 takes a minus sign, right? This is just this term, which goes over here, okay? Now the next one can be written in a similar form as exp of K. Now instead of S1 and S3, I will have S3 and S5. And you can see how already things have become complicated. Why? S2 went away, but now S3 shows up in a very complicated, annoying manner in both the things. So we have decimated the degrees of freedom, but our partition function looks nothing like the simple partition function that we started with. Our partition function has become more complicated, which is the same idea. You know, just because two humans talk in a certain way to each other doesn't mean societies will talk in the same way to each other. It's complicated. and exp of k s3 plus s5 plus exp of minus k s3 plus s5 and so on and so forth. So this looks awful. This partition function looks awful. It's nothing like the simple partition function for the ideal model that we started with. But now the idea is that if we could take exp, but it has a general form. The terms that show up are of this form. They are of the form exp of k multiplied by s plus s prime, and this is not a function, this is multiplication, plus exp of minus k multiplied by s plus s prime, right? That's the general form, where s and s prime could be s1 and s3, s and s prime could be s3 plus s5. If, now this is our wish list, if this thing could somehow be written in the form function of k, where f is some unknown function of the original coupling parameter k over here. So this k we can call as a coupling parameter. It is the interaction strength J scaled in units of KT, okay? So you can see why it's called coupling parameter. If its KT is very high, at a very high temperature, couplings won't matter because the temperature is so high, things won't tend to be coupled. So if this thing could be written in a form f of k multiplied by e of k prime s prime, it looks like an abstract form, but it will become clear in a moment. And if this would be true for all s prime equal to plus minus 1, how many of such combinations are there? 4 combos, right? S is equal to 1, s prime is equal to 1. So s and s prime could be plus 1, minus 1, minus 1, plus 1, minus 1. Should have started a bit higher. So for all 4 combos, what does that mean? So that means s and s prime plus 1, minus 1, minus 1, plus 1, plus 1, plus 1, minus 1, minus 1. So it has to be true for all 4 things. Then our life could be very simple. Why? Because then this means that, and I totally forgot numbering my equations. So where were we? We were, Chandler goes over this in great detail. So once you go through my notes, I request you to go back and read Chandler. I will just call this equation 3 and call this as equation 2. So if you could have this form and we need to figure out what is this function of k and we need to figure out what is k prime. These are the 2 unknowns here because k is given, s and s prime are just variables that take certain value. So it's a kind of strange equation because you want it to follow, you want it to be true for four combinations of values, but you have only 2 variables. So if you recall, you can solve equation of 2 variables. You can solve for 2 variables if you have 2 equations. If you have 2 variables, if you have 4 variables, then you have only 2 equations. You know what I mean? So we'll get to this in a moment. First, let's see what this form will do for us. If you take this form, which is equation 4, and put it to equation 3, your life becomes very simple. How so? So Q of Qn with 4 used in 3 starts to look like summation S1, S3, S5. Remember, we have removed all the even ones. We have removed S2, S4, S6. But earlier we had this e to the power k of S1 plus S3 plus e to the power minus k of S1 plus S3. Now that can be replaced by f of k e to the power k prime S1, S3. So this will become f of k e to the power k prime S1, S3. Now the S3, S5 will also contribute something that looks like f of k e to the power k prime S3, S5 dot dot dot. Now we have a very simple form again. The complication has disappeared, right? Because now this thing, how many f of k's do we have? So if I want to remove all the f of k out and write a power over there, let's figure out that power in a moment, but then this thing will look like k prime s1 s3 plus s3 s5 plus s5 s7 plus dot dot dot. This is very similar to equation 3, right? What power should I put here? Any help? Should it be power n or power n over 2? It will be power n over 2, right? Because if we had n spins, we had n by 2 such pairs. So this term has an extra term that comes up in the beginning, the prefactor. But apart from that, it is the same as the original Ising energy. So you can see that if we could find a solution to equation 4, then it will be possible that the decimated Hamiltonian, the decimated system has the same governing interaction as the original system. So so this is group lots of humans, and we replace the identity, we average over the behavior of every or even numbered human and say that the interaction will still be similar. But for that to happen, these equations must have a unique solution. So that's what we need to figure out. But if that could be true, and we are going to look at that, and you have to take my word that that is really true, then we can say that Q of Kn is given by f of k to the power n over 2 multiplied by Q of k prime of n by 2. And this is the first relation of renovation group theory. This is a recursion relation. It was first derived by Kardanoff. It is called a Kardanoff transformation. So you have taken the partition function of the n system and showed how it relates to the partition function of the system with half the spins decimated. And the idea is that it will look similar, but with a different coupling constant k prime. So now we need to figure that out. So in order to do that, we have to solve for f, which is a function of k, and k prime in equation 4. So there we seem to have a problem, because if you look at this thing, we have a function f and we have a variable k prime. So we have two variables, f and k prime, but we have 4 different equations. So how do we solve for 2 variables when we have 4 equations? It looks like it's going to be over constrained or under constrained. Which one is this? Over constrained, right? You have only 2 variables and you're asking them to, no, you have only 2 variables and you want them to do 4 different things for all possible values, 4 different values. But what happens is that s is equal to s prime is equal to plus minus 1, and s is equal to minus s prime is equal to plus minus 1 give the same equation. They don't give you anything different. And you can see how that happens. So let's work through it carefully. So let's say s is equal to s prime is equal to 1. No, I didn't. I'm still unfrozen. I'm still liquid. If s is equal to s prime is equal to plus 1, then what will happen? This equation will become, this is where a blackboard would have been useful. Let's actually go to the next page so I can write down that equation and work with it carefully. Otherwise, we will all go crazy. So what was our relation? Our relation was e to the power k of s plus s prime plus e to the power minus k of s plus s prime should be equal to f of k e to the power k prime multiplied by s prime. So let's first set s is equal to s prime is equal to plus 1. What do we get? E to the power 2k plus e to the power minus 2k is equal to f of k multiplied by e to the power k prime, correct? Now let's set s is equal to s prime is equal to minus 1. What do we get? E to the power minus 2k plus e to the power 2k is equal to f of k e to the power k prime. We got the same equation. This is same, right? I just switched the order of adding. Addition is commutative, so we didn't do anything funky. Same thing happens with s is equal to minus s prime is equal to plus minus 1. You get the same equation. So first equation we have is this one. So this is equation number 6. The second equation, when you put a minus sign, what will that look like? E to the power k and s plus s prime. What does that mean now? It's 0, right? So e to the power 0 plus e to the power 0 is equal to f of k e to the power minus k prime, or f of k e to the power, this is 1 plus 1 is equal to 2, is equal to 2 multiplied by e to the power k prime. This is our second equation. So yeah, it's possible to solve for it in 1D Ising model. And now you can solve it. It's really trivial. This means that e to the power 2k plus, Siri, go away. E to the power 2k plus e to the power minus 2k is equal to 2 ek prime multiplied by ek prime, or e to the power 2k plus e to the power minus 2k is equal to 2 e to the power 2 ek prime, or this has a well-known name. So we can say 2 e to the power 2k prime is equal to this thing divided by 2. And this is called half ln of hyperbolic cos of 2k. That's a very interesting relation. That's telling us how does the coupling parameter. So this is coupling parameter for n by 2 system where we have removed all the even spins. And this is the coupling parameter for full system, right? And it is telling you that these two coupling parameters are related to a hyperbolic cosine formula only in 1D. This will not happen in 2D. Things are different. And now you can go and calculate f of k. F of k is 2 e to the power k prime. So what does that mean? F of k is equal to 2 square root of hyperbolic cos of 2k. So I'm thinking whether I should do the presentations first. Yeah, let's finish 1D, then we'll start with presentations. So what does this mean? Now, if you think about ln q, which is the log of our partition function, that we know is the free energy. So let's think of the intensive free energy. Let's think of how this thing relates to g of k, where we have defined g of k as intensive free energy. So it is just 1 over n log q. So we showed that q of k comma n is equal to this property, right? So we can take log of both sides, and what do we get? So I should have numbered this equation. This is equation 5a. It's so important, I forgot to number it. So log of equation 5a gives us ln q of k comma n is equal to n by 2 ln f of k plus ln q of k prime n by 2. And if you put in the formula for g of k, this directly gives us that g of k prime is equal to 2g of k minus ln 2 hyperbolic cos of 2k. And this equation is the central. So I told you the first one was the Kadanoff transformation. And this is the central renormalization group equation for 1D Ising model. This is telling you if you calculate the free energy for one interaction, you can go and get the free energy for other interaction or vice versa. You can calculate the free energy for one K and go and get it for another K prime, and you see what is the relation over here. This is super important. Now, why is this super important? Because we can start with a K prime, which is very small. If K prime is very small, let's say K prime is equal to 0. If there was no coupling between any of the spins, then writing the partition function is trivial. Why? If K prime is equal to 0, what will be the value of our partition function? Anyone wants to help me? We have an Ising model. It's not hard, just think through it and it will come in a moment. We have an Ising model where every spin can be plus, down, up or down, and you have n such spins. So what is the value of the partition function? What is the way in which, number of ways in which you can arrange the system? And there is no coupling. How many ways can you arrange one spin? 2. And you have n of them, and they can be arranged independently. So Q is equal to the power n. Therefore, G of 0 is log 2. The free energy, how did I get this? G of 0 is 1 by n log Q, which is 1 by n log 2 to the power n is equal to log 2, right? So we know what happens to the system when there is no interaction energy at all. The partition function is trivial. This is where renormalization group theory starts in practice. It will say, well, I know that for K prime is equal to 0, the Q is, I know the value of G of 0, it's log 2. But what if I assume that the free energy won't be very different from this value if the K prime is not exactly 0, but just ever so slightly from 0. So RG would assumes that G of 0.01 is also approximately log 2. If you're not happy with this, don't start from 0.01. Start from 0.000001. Start from 0.0000001, right? You know, as you make this smaller and smaller, this becomes more and more accurate. This becomes more accurate as K prime goes down, right? So, by the way, who all is left in? So today we have Thomas, Gian, Jess, and Becca, 4 people. Okay, does any of Thomas, Gian, Jess, and Becca object to the possibility of making their presentation on Thursday?
I don't mind either way. I could go today or Thursday.
Okay, great. Thank you, Jess. It's not an airplane situation. If you don't say anything, I will assume that you're okay with it. It's not emergency role. But we will start with you, and it's possible that we don't have time, in which case we will go to Thursday. So, okay, so because I wanna finish this before we lose momentum in this, and then please go read Chandler and all of this. It's very new with a very high likelihood. Most of you have never seen this material. If you have, then that's great. But if you haven't, this is very new stuff, but it's actually really simple. So we know that our free energy per spin is log 2 when the interaction coefficient is very small. But we are not interested in that. We want to calculate the value of this at finite interaction coefficient. So how do we start with this? So for this now, we will use our formula that K prime is equal to half ln cosh of 2K. So we know that K prime is equal to half ln cosh of 2K. It's not cos, it's hyperbolic cos. Or K is equal to half cosh inverse of e to the power 2K prime is equal to half cosh inverse of e to the power 2 multiplied by 0.01 because that's the K prime that we took. This thing you calculate using any calculator. It comes out to be 0.100334. What does this mean? This means that now we can use our central RG equation, that 2g of K, we will take this term and bring it to the left-hand side. So, and let's call it equation 8. So now use equation 8. And what does that tell us? That tells us that 2g of K is equal to g of K prime plus ln of 2 hyperbolic square root of hyperbolic cos of 2K. So now we can use this and calculate g of K for K is equal to 0.100334, right? Because we know that g of K prime, we just calculated it, is ln 2 plus ln of 2 of square root of hyperbolic cos of 2 multiplied by 0.10034, whatever that is, right? It's just a number. It's just a number. That's the key thing here. There is no calculation, profound calculation here. It's just a number. So this gives us g of K is equal to 0.698147. So let's summarize all these algebra math. What have we done here? We have done something really simple. We started with we have basically constructed a ladder of K values. We started with a very small K value, 0.01. And renormation group theory said that for a very small, weak interaction, the free energy, now we are talking about values of g of K. Renormation group theory said that the value here is just ln 2, right? How did we do that? We said that 0.01 is almost like no interaction. So the partition function is 2 to the power n. So the free energy is given by ln 2. What is the exact value for this one? Clearly we made an error, right? That's not really true. So we made an error here. The exact value actually, so if you take this ln 2, this is log of 2 is 0.693147, and the exact value is 0.693197. So it looks like a small error, but it actually starts to get even better and better and better. Now from this, we used our formula for K prime is equal to half of this thing, and we've got a value of K, which was 0.1, right? It was 100334. I'm just going to write it 0.1. Then we calculated this G of K, and it happened to be 0.698147. Here, if you wrote down your Eyring model and used the stuff for which Onsager was given Nobel Prize and everything, actually calculated, you will get the answer as 0.698172. Now you can use this again in this formula. Instead of 0.01, now you use this value, 0.1. And this, the next step will be 0.327. And you will keep iterating. And as you keep iterating, you will see that at some point it becomes exact. Once you get to K equal to 2.702146, the value you get from the renormation group looks like 2.70663. And this on the right-hand side becomes the exact value becomes 2.706634. It becomes more and more accurate as you start doing that. So what have we done here? We have increased the K. At this point, you're probably lost as to what on earth does it mean to increase K. For that, let's go back to our formula where we introduced K. K had temperature in the denominator, right? So increasing K means decreasing temperature. So as we decreased the temperature, renormation group theory became more and more accurate. So what have we done here? We have, in a way, constructed something that is the essence of renormation group theory. It's called a flow diagram. We started from K is equal to 0. K is equal to 0 can be thought of as very weak coupling or very high temperature. And we calculated the free energy or the partition function of the system What was the partition function? It was 2 to the power n, right? So the free energy per spin was log 2. From this, we went to some other k, which came out to be 0.1. From this, we went to some other k, which came out to be 0.327. And you have to take my word for it. You have to plug in the numbers to see it actually happens that. It's quite easy to do that. And we kept doing this. In 1D, you can keep doing this operation and you will get to any value of k you want. You will reach k is equal to infinity. Why? Through simple use of equation 7a. Equation 7a will allow you to take a value of k, get a larger value of k prime. This is a monotonic increasing operation. Anytime you put in a value of k, you get a larger value, or maybe I said it opposite. Anytime you put a value of k prime, you get a larger value of k. You will keep on churning it and get larger and larger and larger and larger values. It will take you to k is equal to infinity. What does this mean? It means there is no phase transition. You can solve for the average magnetization, for the free energy, nothing changes. You get the same physics irrespective of the temperature that you used. You started at a very high temperature and you go to a very low temperature and the physics does not change. The flow diagram is preserved. This is pretty much the end of math of renormalization group that I'm going to show you in this class. This material should easily take quite a lot of time. So don't be harsh on yourself if it all seems a bit confusing, but please go and read, and don't be harsh on me as well if it seems a bit confusing. Go and read Chandler and it will make more sense. The point I want to make you next is something which I won't do right now, but I will refer to you to Kardanov's paper, which I'm going to post online in American Journal of Physics, where he shows this decimation operation for a 2D Ising model. So how will 2D Ising model look like? Let's say a 2D square Ising model, right? So here decimation is a bit tricky. How do you decimate things? What does even and odd mean? It's a bit tricky, right? So what he does here is to decimate these ones. Okay. Now the partition function is a bit complicated. So you can see you still have a square lattice, but it's rotated by 45 degrees, right? You still have a square lattice, so you have hope that maybe the physics will be the same. Remember how when we started doing it, we landed with a partition function, which looked awful, this ks from s plus s3. And then we wrote down this equation and we showed that, oh, maybe it does work because we did get a solution for those equations. So here also it will work because when you decimate these ones, you end up with a square lattice rotated by 45 degrees. And you can do all this business and get a similar flow diagram, but something very funky happens in 2D. In 2D, when you construct this flow diagram, you get a discontinuity. You get a value of the coupling constant Kc. And depending on which side of the flow diagram you start from, you will not be able to go across Kc. So here, we will be able to move from k is equal to 0 till Kc, but then, and again, this is interesting and you have to go see Kardanov's paper to really see why this happens. But you get a discontinuity at k is equal to Kc. So it predicts a phase transition. You don't have uninterrupted flow. You have interrupted flow, and that's a phase transition. And you can solve this thing just like we constructed such a table. What you would do here is to, if you got those equations, which I didn't show you, you could start from a small value of k, and you would see that you get stuck at a certain value of Kc. You could start from a large value of k, and you would again see that you get stuck at a value of Kc. These values of Kc won't be the same, but you know that the critical temperature is now going to be somewhere in the middle of these two Kcs. That's your critical temperature, and that's why it works. In 3D, it gives you the value of, it's an approximation, it's not exact. This scheme works for complicated Hamiltonians and everything. People use it for a variety of things. I like it a lot because some people think that when you construct a deep neural network, the reason a deep neural network does such a good job is because every layer is actually decimating degrees of freedom. Every layer corresponds to a renormalization group type operation happening. So there is a paper by Schwab and Mehta. They are physicists at Northwestern or Northeastern. I always confuse which one they are. They sound so similar, but one's in Chicago, one's in Boston. Schwab and Mehta have a paper where they show that we can explain why deep neural networks work by thinking of renormalization group. You can go and see that paper if you want. I can send you the reference if you don't find it. But it's the same idea here that anytime you take high dimensional data and pass it through a bunch of neurons to go to a lower dimension, you're kind of decimating spins. So in a sense, a deep neural network is recovering the renormalization group structure. This is where I'm going to stop, RG. Next time, I will introduce you to another kind of advanced topic. There should not be any hyphen, but that's something you will more likely use in your work. It's called Monte Carlo simulations. And I will introduce you to possibly one of the most famous algorithm in computational physics, which is called the Metropolis algorithm from 1950s. And I will show you how it works. And it's quite simple, and it's simpler than the stuff we saw today. You will actually also see what happens when in MATLAB you call the norm function. How does it actually generate a random number from a given probability distribution? It kind of uses this algorithm. We'll see that. So in the remaining time, let's go through presentations. Since Jess volunteered, let's start with Jess actually. Okay. And I won't have official office hours from Thursday, but I'm more than happy and excited to discuss any of these things with you, not just in this semester, but also when the semester is over. Just send me an email. I'm always happy to talk. So let's do a screen share. So Jess, I will open up your, I will open up your presentation. So. Oh, where did I keep it? I forgot now. Wait, sorry about that. This is yours, I think. Sorry. There we are, 4 of you. No, that's your midterm, sorry.
The midterm 2 presentation on the right there, I think is it.
This one, right?
Yeah.
Perfect. Upload your presentation. Now we have it. Perfect. Sorry about that. So this is Jess. Okay, Jess, your time starts now.
Okay, so I decided to look at the alchemical perturbation methods in medicinal chemistry paper. Next slide, please. So an important thing in drug design is looking at how proteins and ligands bind. So you can think of a ligand as a small molecule and a protein as the target molecule. And essentially the ligand goes from a free state in solution to a bound state where non-covalent interactions hold it to the target molecule. Next slide. So crystallographic methods can give you information about the structure, but the structure alone does not provide the information that you need about binding affinities or binding strengths. So you need to use various methods for determining binding affinities. And alchemical free energy methods is one of those, which this paper gets into. So the free energy of binding is shown by that, that equation, where the partition function for the free macro state and the partition function for the bound macro state are included in there. And that's just the same partition function that we know and love from this class. Next slide. So in general, molecular dynamic simulations, you can use them to model the behavior of atoms and molecules. You apply what's called a force field, which is a fancy word for parameters that you provide during a simulation. They applied classical Newtonian laws, and there's a bunch of factors that affect the quality of the simulation. And if you get all these things right, like the force field, which is the environment that the molecule is in, and the shape and the size of this periodic boundary condition, and if we hold pressure or volume constant, it can provide like ease of calculation for things like free energy because it holds it in a particular ensemble. Next slide. So they go over multiple types of free energy calculations. An unbiased simulation is where you just allow the ligand to freely travel from unbound to a bound position. And that takes forever. It takes a lot of like computational time. So they use a steered MD simulation, which is where they use a force to pull the ligand away from the binding pocket. And that requires a lot of non-equilibrium data that you would eventually kind of extrapolate equilibrium energy information using Jarzynski relation. And then umbrella sampling is when you kind of pull the ligand away from the binding pocket at discrete positions, so that way you can kind of more directly get equilibrium information. And then they get into a lot of alchemical perturbation, which is what this paper is really about. So next slide, please. In general, this is just my poorly drawn rendition of what a figure that was in the text. So this is just an example of an alchemical transformation where essentially what happens is you take a molecule and you decouple it from its environment by changing the atoms into dummy atoms. And so this can give you information about the environment interactions versus non-interacting, like with a vacuum. Or you can change a molecule from, let's say, ethane to methanol, and this can give you like maybe solvation energy differences. So you can get all this information by just replacing a couple atoms with these non-interacting atoms and decoupling it. And so they do this. Next slide, please. They do this in this paper, and there's different types of free energy perturbation calculations. So there's absolute versus relative. Absolute is when you take the ligand and decouple it from the solvent, and you take the bound ligand and decouple it from the protein. And that's not as accurate as relative, where you take a pair of ligands binding to a protein, where one ligand is transformed into another in both the solution and on the protein. So because the relative is more, it's less different between the final and initial like states, it's more accurate of a calculation. Next slide. And these are just like papers that they, in practice, they gave examples, and I just kind of wanted to show these values of how far away from the actual experimentally determined values they were. So it's pretty remarkable that this relative alchemical perturbation in this first paper, they got within 0.5 kcals per mole, which was actually the theoretically allowed limit of accuracy. So they got it as good as they could possibly get it, which is, I thought was really cool. And then the second paper, they got pretty close as well. That was a giant study. And then next slide, please. And then just two more where I just really wanted to show those values of how close they could get to the actual value. Next slide. So in conclusion, this is important for lead compound generation, where when we increase the computational abilities, we can start doing these types of calculations and apply them in actual the medical field. And that's all I have.
Okay, thanks, Jess. Who wants to go next? Thomas, you want to go?
I can go.
Okay, Becca, great. Is this you, Becca? Yeah, that's Becca. Okay, Becca, your time starts now.
Okay, so hi everyone. I wrote a report on paper 2, like a lot of other people did, but this paper is on free energy perturbation methods for drug design. I chose this one as I've worked in healthcare in the past and I have a strong interest in medicine and the interactions of drugs in the human body. So this paper discussed, you can go to the next slide. Next slide. So this paper discussed ligand protein interactions which occur when a ligand in free solution meets a protein and binds with it. to characterize the binding free energy, three things are required and need to be understood. These in the paper were listed as the number and energies of the free states, number and energies of the bound states, and the protein, ligand, and solvent structure and energies. So predicting both the ligand to protein binding poses and affinities is extremely important to lead drug design. Just simply examining the structure doesn't provide information about the drug compound, affinity, potency, efficacy, etc. So next slide. A lot of methods exist for doing this. This paper specifically focused on alchemical perturbation methods for calculating the free energy. In this section of the paper is what I largely focused on. These methods are called alchemical because they involve these non-physical transformations of a ligand into either a non-interacting dummy state or into a different ligand. I depicted this in this illustration by transforming this little ghost guy into this little guy wearing a different hat, or this little ghost guy into a ghost, and then into a guy wearing two different hats.
Your thing is almost as cool as Suhas's cool cat and French cat.
Thank you. In this transformation, the goal is to transform smoothly from the initial to final states into a number with a number of lambda states to limit the free energy changes between steps. So again, two methods. There's the relative and the absolute. The absolute is the one that would turn it into this dummy atom, which is the little ghost guy, and the relative turns it into a guy wearing a different hat. And in both cases, the difference in free energy is found between the states, but not the value of free energy itself. The first is called like a delta G, and the second is a delta delta G. I just lost my train of thought. But in large, the relative method tends to be more accurate, as the final state is more similar to the initial state, as some people have already mentioned. You can go on to the next one. And so then the paper went into detail and looked at several papers, including specifically 4, which largely use relative techniques, though one did use absolute alchemical methods. All the papers demonstrated an ability to examine large data sets and produce fairly accurate and reliable results, with some limitations in sampling, oversimplifications, and some other issues. They were largely limited by the fact that most of them were retrospective studies, when a large drug design requires prospective studies. In particular, this is an issue for studying small novel molecules. One of the papers was a prospective study and did show significant potential for the alchemical method with binding free energy calculations within 1.1 kilocal per mole of experimental results. But in large, all the papers, even the one that used the absolute method, demonstrated results with feasible room for improvements and movement towards implementing alchemical methods for computational drug design modeling. Right, that's it for me. Thank you.
Okay, thanks. So that leaves Jion and Thomas. And so we will finish your presentations next time. And if you really object to that, then we can arrange another time and we can just do the student, and so either Thomas and me together or Jion and me together, if that's what you prefer. If next time is a difficult thing for you. Otherwise, see you on Thursday.